Here, we will look at experimental design, precise measurement, and applying the scientific method effectively. This session will help you understand the practical aspects of conducting experiments and interpreting results to advance scientific knowledge. Let's get started. Let's take a closer look at how the scientific process unfolds. It starts with making observations, where we look for patterns or any discrepancies in the natural world, recognizing that the universe exists independently but is accessible to human experience. From these observations, we develop hypotheses and models, which are provisional and testable explanations designed to account for the patterns we've noticed. Then we conduct experiments to test these hypotheses. This is followed by a crucial step called falsification or validation, which is the foundational rule in science. While a theory can't be proven with absolute certainty, it can be disproven by a single strong counterexample or experiment. Through this cycle, consistent findings lead to theories and laws that help us understand and predict phenomena reliably. This ongoing process is what drives scientific knowledge forward from simple observation to established law. This diagram lays out the core steps in the scientific process, starting with observations, where we look for patterns or unusual trends in the world around us. From these observations, we develop hypotheses or models. These are provisional ideas that can explain what we've noticed. Next, experiments are designed to test these hypotheses. After gathering experimental results, we move into a phase of falsification or validation, which is crucial because a theory can never be proven with absolute certainty, but can be disproven by a single counterexample. If a hypothesis withstands these tests over time, it may contribute to forming broader theories and laws that describe natural phenomena. This cycle ensures our understanding evolves based on evidence and critical testing. Let's look at an example where we investigate how the frequency of stationary waves on a string changes. In this case, we can vary the tension by adjusting hanging masses or change the length of the string as our independent variables. The frequency of the stationary wave is what we measure as the dependent variable. To ensure accurate results, we must keep certain factors constant, like the mass per unit length of the string and the environmental temperature. If we don't control the mass per unit length, say by using different types of strings during the experiment, it compromises the relationship we're trying to observe between tension and frequency. This highlights why isolating variables and controlling conditions is crucial for reliable conclusions. It's important to understand the difference between hazards and risks when assessing safety. A hazard is something that inherently has the potential to cause harm, like a Class 3B laser. Risk, on the other hand, is about how likely it is that this harm will actually happen, such as the chance of retinal damage from a stray laser reflection. When it comes to legal responsibilities, simply copying a generic risk assessment isn't enough. Physicists need to create what's called point-of-use text, which means tailoring assessments to the specific conditions of their lab. This involves checking if local safety measures like fume extraction or shielding protocols for radiation are adequate and making sure everything is set up correctly to protect everyone working there. Let's now focus on understanding the difference between accuracy and precision in measurements. Accuracy refers to how close a measurement is to the accepted or true value, like hitting the center of a target consistently. Precision, on the other hand, is about how consistently you can repeat the measurement, regardless of whether it's close to the actual value. It's about how tightly your results cluster together. Alongside these concepts is resolution, which is the smallest unit an instrument can measure, like 0.5 millimeters on a ruler. This defines how finely you can read each measurement and sets the baseline for the uncertainty in a single reading. Understanding these distinctions helps ensure we interpret measurement results correctly and improve our methods when needed. Now, let's take a closer look at the two main types of experimental errors. Random errors cause unpredictable fluctuations in our measurements, which makes our results less precise. These happen due to small, uncontrollable variations in the experimental setup, but they can be minimized by taking multiple measurements and finding the average. On the other hand, systematic errors are consistent biases built into the method or the equipment, leading to inaccurate results. These errors aren't fixed simply by repeating measurements. Fixing them usually means recalibrating equipment, applying mathematical corrections, or even changing the experimental method itself. Understanding these differences helps us improve both the reliability and accuracy of our experiments. Let's consider a common example of a systematic error when measuring the volume of a metal cylinder with a micrometer. The issue here is that the micrometer shows a reading of 0.12 millimeters even when the jaws are fully closed. This zero error means every measurement taken will be off by that amount. For instance, if a student measures the diameter as 5.50 millimeters, the actual diameter is 5.38 millimeters once you subtract the 0.12 millimeters error. Since volume depends on the cube of the radius, not accounting for this small error leads to a significant miscalculation in the volume. Simply repeating the measurement many times won't fix this problem. The only way to get accurate results is by either calibrating the instrument correctly or applying a mathematical correction to account for this zero error. Now, let's focus on how we handle uncertainties in measurements. Every measurement carries some doubt, which we call uncertainty. First, we have absolute uncertainty, which is simply the margin of error in the units we are measuring, like plus or minus 2 millimeters in a length of 115 millimeters. To compare uncertainty across different measurements, we use fractional or percentage uncertainty, calculated by dividing the absolute uncertainty by the measured value and converting it to a percentage. In this example, that's about 1.7%. When dealing with calculations involving multiple measurements, like finding volume from length, we need to combine the uncertainties by adding their percentage values. This helps us understand how errors can build up and ensures we have a realistic sense of confidence in our results. This graph shows how we analyze data by plotting the dependent variable against the independent variable and fitting a line that represents their relationship. The gradient, or slope, tells us the rate of change between these variables, following the equation y equals mix plus circa. If the intercept is not zero, it can indicate systematic errors because a directly proportional relationship should pass through the origin. The uncertainty bars help us estimate the margin of error by allowing us to draw lines with the greatest and least possible slopes, which accounts for variability in our measurements. This approach helps us understand the reliability and accuracy of the data trends we observe. Now, let's focus on how to distinguish signal from noise by spotting anomalies in data. When we look at a graph like this one, most data points align closely with the expected trend. However, that one point way off to the upper right signals something unusual. The process for dealing with anomalies involves 3 key steps. First, identify whether a data point falls clearly outside the expected margin of error. Next, investigate why it's there. Could it be a random blip, a fault with the equipment, or is it revealing a new physical phenomenon we haven't seen before? Finally, justify what to do with the anomaly. Scientific integrity requires that we don't just remove these points without good reason. Any decision to exclude or include such data must be clearly justified and documented so that our analysis remains transparent and trustworthy. This approach helps ensure that we separate meaningful signals from random noise in our data. When evaluating results and drawing conclusions, it's important to check if the outcome matches your original hypothesis and prediction. Next, put your findings into the proper scientific context by comparing them to accepted reference values or previous studies. Finally, be clear about the limits of your results, including any uncertainties, methodological weaknesses, or assumptions you made during testing. It's important to approach conclusions with caution and avoid overstating certainty. Let's take a moment to consider how the scientific community works together to filter out bias. A single experiment on its own doesn't prove anything until it has been carefully examined by others. First, the experiment undergoes peer review, where experts check the methods and findings for accuracy, bias, and ethical standards. Then, it is evaluated against agreed conventions, shared rules and standards everyone follows in the field. After that, the findings must fit within a shared terminology, ensuring that the information is communicated clearly and consistently. Through this process, only the most reliable and well-vetted knowledge becomes accepted by the community, building a strong foundation that others can trust and build upon. This collaborative approach helps ensure science remains objective and trustworthy. When we talk about the ultimate test in experiments, we look at repeatability and reproducibility. Repeatability means getting similar results when the same person uses the same equipment and method within a short time. This shows that the measurement is precise and consistent inside a single setup. On the other hand, reproducibility takes it a step further by involving different people, different equipment, and even different methods, yet still arriving at similar results. This proves that the finding or physical law holds true universally and isn't just a coincidence or specific to one particular setup. Both are important, but reproducibility is what really confirms the fundamental truth of a result. This image shows how the process of discovery in physics is continuous and never really comes to a full stop. Each discovery raises new questions, and every answer leads to more exploration and new hypotheses. This cycle keeps expanding our understanding, reminding us that even the most accepted laws are always open to challenge if new evidence emerges. So discovery isn't about reaching a final conclusion, it's about ongoing learning and growing knowledge. With that, we wrap up our discussion. Thank you all for your attention and engagement.